Like I was saying, we literally are doing the last new stuff today. I am pretty sure if you were here on Friday, you have all of this. Am I correct? Page 31 is filled in for you guys. Oh, okay. Yep. And that's all. So we just said ignore this until chapter 6, I think I said. You don't need to write any of this in. I'm going to show you what I'm talking about here. But like I said, please ignore the map symbols. We will not talk about them at all this chapter. You do not need to understand them for this chapter. It's super easy, but we're just not doing it at all for this chapter. And the kicker is this is not what the rocks look like. There is no rock out there with a bunch of little H's in it. It's just not what the rock looks like. It's the symbol whoever made this chart decided to use for that rock. It has nothing to do with what it looks like. All right, so that's that. Just like with all three rock charts, the texture I think is the most confusing. So in igneous rocks, the texture were glassy, fine, coarse, and very coarse. And it had nothing to do with how they felt. It had to do with the crystal size. For sedimentary, our choices were clastic, bioclastic, and crystalline. And again, it had nothing to do with what the rock felt like. Now, again, with metamorphic, we've got foliated and non-foliated, nothing to do with how it looks. If you remember on Friday, to help you remember what the word foliated means, I started to fold the paper. And what did I create by folding the paper? Layers. So when you see foliated, I want you to think of layers. So when you're holding the rock in your hand and you can see layers in the rock in your hand, that is a dead giveaway. It's metamorphic. Not to be confused with the layers we talked about in sedimentary rocks. Last week, I showed you a picture of the Grand Canyon and how there were layers of rocks in the Grand Canyon. Sedimentary rocks form in layers. So you will find underground. In fact, if we dug up this whole little grassy area here and just stripped away all the dirt, we would most likely find a layer of shale underneath it. I'm not positive, but knowing what's around most of Western New York, we'll most likely find shale, maybe some limestone, maybe some rock salt, depending on exactly where we are, but we'll find a whole layer. And this is true in Minecraft. When you are digging below ground, you will hit bedrock and it is formed in horizontal layers underground. Minecraft is good sometimes. So it kind of helps to remember. Like I was saying though, when you're talking about layers, if you're holding a rock in your hand and you see layers, metamorphic. A lot of people just hear layers and they want to think of sedimentary, but the rock in your hand, if there's layers, is metamorphic. If you do not have this whole thing, make sure you get it because it's a lot of good information here. So what we're going to do then is just get the last bits of information you need about metamorphic rocks, and then we are done with this chapter, and we'll just practice until we take the test. As with all three rock layers, you have to be able to tell me, how do metamorphic rocks form? That always comes back to the rock cycle. How do we use the rock cycle to figure out how a rock forms? Okay. Read it backwards. So for example, we're going to metamorphic rocks. Read it backwards. So I could read this arrow backwards. Metamorphic rock comes from a sedimentary rock that gets heat and or pressure and turns into a metamorphic rock. I could read this one backwards, and it comes from an igneous rock that gets heat and or pressure and turns into a metamorphic rock. And then there's also this one too. This one saying one metamorphic rock could get heat and pressure and turn into a new metamorphic rock. So right at the top of page 33, right next to it looks like a banner or a flag on page 33, it says metamorphic rocks. This goes right underneath that on page 33. We've got metamorphic rocks are existing rocks that are changed by heat and or pressure, and that's called metamorphism. I just wrote heat and pressure heat here. You probably should officially say heat and or pressure. So I think did I talk about the Hershey bar with you guys or no? Okay, perfect. Good. I'm not going to tell the story twice. Can you guys picture a Hershey bar right now? What's it look like? Rectangle. What's on that rectangle? More rectangles. So you're pitching like a full size one.
Yeah.
So if you're thinking about like the little ones that you guys got for Halloween, perhaps, let's talk about like a full size one that you would get at like the drugstore or whatever. So you've got a rectangle that's broken into little rectangles, and what's on each rectangle? The word Hershey, right? You guys all picture that? Okay. So we're going to heat that rock, or that, well, I guess it's a rock in my brain. But we're going to heat that rock up by putting it in your car in August. Oh. What happens to that Hershey bar? Ooh, okay, some of you said melts. What is melting? What's it turn into if it melts?
Nothing then.
Liquid. So what can liquids do? They can reform, but what I'm getting at is liquids pour out. Like liquids, that's liquid. Does your Hershey bar turn into a liquid on your car to heat in August? No, it doesn't melt. I know why you said melt, but for this, we need to distinguish that melting means it turns into a liquid. So your Hershey bar doesn't melt in the car in August. What does it do? It's mushy. I call it ooey gooey. You can call it mushy. Ooey gooey sounds more flavorful. It's ooey gooey. Now, what does it do at nighttime? It reforms. Hardens. By the way, that's called recrystallizes. Do you guys know what the word crystallize means in the first place?
Yeah.
Can you figure? Turns into a.
Back into crystal.
So crystallizes itself means to harden or turn into crystals. So originally, before the Hershey bar was a Hershey bar, like in the Hershey bar factory, what was it in the Hershey bar factory?
Liquid.
It was a liquid. They melted all the ingredients and it was a liquid in the store or in the factory. Then they put it into molds to make the Hershey bar. And then it hardened, it crystallized. So that's kind of like an igneous rock there. And then you put it on your car seat and it turned into ooey gooey. And then it cooled again. Does it look the same now that it's cooled? No. What's happened? Because it was ooey gooey. Yeah, it's taken whatever form that ooey gooey fit. Now, would you maybe be able to see some of those rectangles?
Yeah.
What would they look like? Would they be perfect rectangles still? They'd be deformed. That's the perfect word. You might still be able to recognize, and maybe the word Hershey that was perfectly printed originally, maybe instead of like a perfect H, now it's all like twisted and messed up, but maybe you could tell it was an H, maybe not. That is metamorphic rocks right there. We could add to that. Let's say when it was ooey gooey, you sat on it.
Ooh.
That was
bad day.
Because that's heat and pressure now. So what happens when you sat on it? You've now smushed it, and when it cools and hardens again, it's going to be whatever form it was when you smushed it. Those are metamorphic rocks. Here, I have a rock example of that same scenario. Here is a very nice piece of granite. It's actually been cut and polished, so this should look like granite countertops. I wouldn't want this one as my countertops. That pink is kind of a gaudy, ugly color. I wouldn't want in my kitchen, but to each their own. But anyway, So we got a metamorphic rock. Do you see the big, beautiful crystal just from where you're sitting?
Mhm.
Let's focus in on like one of these black ones. This, because you can see that contrasting very nicely from wherever you're sitting. Let's make this rock ooey gooey. By the way, how do we make a rock ooey gooey?
Heat.
Heat. Heat and or pressure. Now, do we melt it? No, that's different. We're just heating it up. So we're heating up a rock and it's becoming ooey gooey. What's gonna happen to that pretty circular looking black crystal right there when it gets heat? So it gets ooey gooey and then pressure. Somebody sits on it. It's gonna change. What will that pretty circle shape end up doing? It's gonna squish, it's gonna flatten out. In fact, where the heck did my, oh, there it is. It will turn into this rock. So can you see that these rocks might be related?
Yeah.
What makes you say they're kind of related? Same colors. You can see the pink, the black, the lighter pink. There's some whitish colors in here. This, by the way, this is the metamorphic rock gneiss, is what happens when you take granite, make it all ooey gooey, and then squish it. That black, what was a circle on here, has squished out and elongated. It got, like the word that Carson used, distorted. We take what was nice and pretty crystals and we distort them into these weird shapes, just like the Hershey bar. So I hope that helps. Can you, like I said, you can tell they're related, but are they identical? No. So they do retain some of their characteristics, but not all of them.
So like the color will never change.
Right, the color's not going to change. Like you will still find all of the colors that are in this, in this. Now, some aren't as obvious as that. Here's that sample of shale that I was looking at last week with the big fossils in it. What is this gonna end up like, gonna look like when, are there different colors in it to begin with? Not really, there's a few different shades of gray, but it's mostly just gray. What's gonna happen when we heat this one up? It's just gonna be gray. It's gonna turn into slate. You will end up with different layers, but because those layers are all the same color, you won't be able to see those different layers. Well, you'll see them, but they're not as obvious as the striped one. All right, so what changes take place for that second set down, changes in rock due to metamorphism? So metamorphic rocks have a different appearance and chemical composition from their parent rock. By the way, we should probably define a parent rock. It's the rock it used to be before heat and pressure. So we're right here where it says changes in rocks due to metamorphism. So parent rock is a vocab word you are responsible for knowing. I think I mentioned last week that I know you don't want to think about it, but again, you came from your parents, just like that sample of gneiss came from granite. So granite is the parent of the rock gneiss. Nice, yeah, it's a nice rock. Gneiss is the last one on the foliated rock chart. It's foliated banding. That's gneiss. I know it doesn't look like it's pronounced nice, but it is.
Yeah.
And the other one, piece of schist. Yes, my favorite. All good with that slide? I know we also talked about regional versus contact. So for regional, this is going to cause large scale deformation. So the rocks get deformed over a large area. And we can have a high grade metamorphism. That just means high grade means there's been a lot of metamorphism. It's been a big change. So building a mountain, I mentioned this last week, those two plates bumping into each other like this is causing a boatload of heat and pressure. And it's over the whole area where these two plates are touching each other. So we're going to have a lot of heat and pressure over a large area. So that's why it's regional and high grade. Contact is different. This is when the example I gave was burning Riley and Carson's shoulder last week. I was hot lava. I walked through and I burned their shoulders, but their toes were fine because I was only touching their shoulders with the hot lava. That is considered contact metamorphism. This drawing here is a perfect example of how contact metamorphism works. I'll let you guys finish writing before I keep talking. So what I was saying is this drawing should be a perfect example of contact metamorphism. So hopefully you can see what's going on here. There's a small volcano forming here on the surface, and we've got the lava sneaking up through the different layers of the earth. We got the hot magma down here, and it has burned through. So this area right down the center, that is hot lava. When that cools and hardens, it will be an igneous rock. But that hot lava is touching these layers, these yellow and tannish layers around it. That hot lava is going to, I kind of call it cooking them or burning them. My best example of this is when you make s'mores. When you make a s'more and you put your flaming hot chocolate or your flaming hot marshmallow on the chocolate, does it melt the chocolate? It's ooey gooey. And then when you leave that s'more to cool for a second, what happens to the chocolate again? It hardens, it recrystallizes. That is contact metamorphism. So these rock layers that are just touching that hot lava, it's not going to be hot enough to melt them, but it will change them and make them ooey gooey around the edges. And then when they cool and harden, there'll be brand new metamorphic rocks. So when this whole situation cools, down here, this magma chamber, what kind of rock will this magma chamber turn into?
Obsidian.
No, can't be obsidian. Why can't it be obsidian?
Underground.
It's underground. By the way, when the region says type of rock, you only have 3 choices: igneous, sedimentary, and metamorphic. Let's try this again. This magma chamber will be an igneous rock eventually. So will this bright red tube. That will also cool and harden into an igneous rock. What are these rocks? The tan yellow, tan gray. What type of rocks are these? What is a dead giveaway that these were sedimentary?
Layers.
The layers. See how they're formed in layers. Right where the hot lava, the bright red, is touching those layers, so it's turned into like a faded red. When that cools and hardens completely, that'll be a brand new metamorphic rock. So anytime igneous rocks are found next to sedimentary rocks, there will be a small layer of metamorphic rocks in between the two, where the hot lava contacted the rocks that were already there. This isn't a rock, this is a whole mountain range almost. This is a whole land area. So this is like covering, like this is a volcano. So you can see that tiny little triangle is supposed to be a volcano, which is huge. Like we're talking like miles. Good. I'm glad we cleared that up though. So no, that's why like earlier when I was talking about a rock in your hand, that can only be one type. All right. For the next part, what we're going to do is I'm going to have you cross off this picture here. But while you're crossing it off, I'll point out, take a look at the symbols that are used. Those are the map symbols that I was talking about earlier. We're crossing it off because we don't need to talk about it until chapter 6. But this is what they'll do with those map symbols. So you can see we've got bricks. That's limestone. Some polka dots. That's sandstone. This is shale up here. So that's what it'll look like when we do use the map symbols. But for this chapter, you don't need to do them at all. Then over here on this section, we're going to title this section Agents of Metamorphism. And there's going to be 2: heat, obviously. And then the second one's going to be pressure, but I don't want to write that until you know how far down you need to go. But the first bullet we're going to put here is heat. So this whole area is going to be titled Agents of Metamorphism. And there are 2 agents of metamorphism. So heat is the first one. What does heat do to metamorphic rocks? Just like we've been talking about this whole time, heat makes rocks recrystallize. So it makes them ooey gooey and then has them harden. So that's called recrystallization. Makes them harden again. So the crystallization means they turn into crystals or hard crystals. And when we add the it means it happens again. So you take granite, which has already been crystallized once, ooey gooey it up and cool it down again. It's going to recrystallize. It's going to turn hard again. And then finally, Carson's already told us this. Pressure is increase in pressure causes minerals and crystals to elongate and flatten, or like Carson said, deform. Right. We've got just a couple sentences, not even a sentence. Yep, basically. Top page 34. Classification of metamorphic rocks. You should be able to look at the metamorphic rock chart and tell me how scientists classify metamorphic rocks. What's the first thing? And let's make 3 groups. Texture. When they ever ask, how are they classified? Always go with the first thing that puts them into groups. So with igneous rocks, the first thing was whether they were intrusive or extrusive. With sedimentary, it was whether they were classic, crystalline, or bioclastic. And now we're going with, again, texture, which is, so they're classified by texture. Whoa, that's messy. Texture. And that includes whether they, here, I'll just put it up here so it doesn't keep changing like that. It says texture, foliated, which does include banding and mineral alignment, and whether they are non-foliated. So foliated and non-foliated, including banding and mineral alignment. And then the last thing is the degree of metamorphism. I kind of like to think of this, you guys heard of first, second, and third degree burns? That's a lot like this. A first degree burn's not a bad burn. Like a sunburn is actually a first degree burn. Your skin has changed a little bit. But then those burns could get worse depending on the heat and how long that heat was on. I also like to think of this as toast. There's lots of different degrees of toastedness, right? You could have light brown, barely toasted, into char doesn't even really resemble the toast you were originally put, or the bread you originally put in. So degree of metamorphism, it can be small or major changes, and it all depends upon the amount of heat and pressure. Yeah, oh yeah, just like the s'more. So depends on how much heat you give that marshmallow again. You could either have one that's barely changed at all to one that is black and doesn't even resemble the original marshmallow you were using. Same is true with rocks. Some are barely changed from what they used to be, and some barely resemble what they used to because they had more heat and pressure. Now, parent and daughter material, we already defined parent, so I'm not gonna make you write it again if you don't want to. It's what the rock used to be before heat and pressure. So if you do want to put it in there, parent material is what the rock used to be before it changed. And then the daughter material, I don't know why they don't just call it kid material or child material. I don't know if it's changed now that things are more politically correct, but daughter material is the metamorphic rock after the heat and pressure. They don't care about sons, apparently. I didn't make the rules. Now, I also don't have any sons, so it does kind of seem like I made the rule, but. And then finally, the deeper underground, the more heat and pressure, and therefore the greater the change. So slate is low metamorphism, while gneiss is a high metamorphism because it is found deeper underground. Before you start your homework, I want to make sure you can answer those 4 questions on the bottom of page 34. Yeah, no, I'll wait, sorry. Okay, so on the bottom of page 34, we have, where is my packet? There we go. I'm asking you to find the parent rocks of these rocks that are on here. I will tell you, you can cross off gneiss because it's not on the reference table. And phyllite is not on the reference table. Everything else you should be able to do from the reference table. Do you guys want to do one together?
Sure.
Okay. Wants to know who the parent of shale is. So where should we look? Yep. So did I say that wrong? We want to know who the parent of slate is. So which column will tell us? Nope. Comments right here. Composition tells you the minerals that are in it. The comments will tell you who the parent is. So we find the box slate, and it says it's a low-grade metamorphism of shale. That means you give shale some heat and pressure, it will turn into slate. See if you can do schist, quartzite, marble, and metaconglomerate. Metaconglomerate needs you to use your brains, though. So get those right off the comment section for all of those. Anybody stuck on them? With meta conglomerate. Let's think of that name. Meta conglomerate. Yep. And what's the meta part mean? No, meta is like metamorphic. So what do you think the parent of meta conglomerate is? Just conglomerate. It's a tricky one. I will tell you that's not on the Regencies either.
That's all.
No, all four of these questions. All of them. All right, just make sure we get done. Who's the parent of schist? Schist. Yep, says from metamorphism of clay or feldspar. How about who's the parent of quartzite? Quartz sandstone. Right in the comment section. You can't miss it. So you go to quartzite, metamorphism of quartz sandstone. How about marble? Okay, that one does have two, limestone or dolostone. Like I said, metaconglomerate will not be on the Regents. I just thought you could probably figure it out. Now, phyllite. How do we figure out the minerals in phyllite? Composition. If the bar is there, then that mineral is there. So phyllite, there's a bar for garnet. There is a bar for amphibole and feldspar, quartz, and mica. So basically, it's all of them except for pyroxene. Sure. And how about schist then? What mineral may or may not be? That's the pyroxene. And then finally, name the rock type that is produced when various rocks are changed by nearby magma or lava. It is metamorphic. I would have accepted that, especially since the way I worded it. I do want you to see that Hornsfeld is made from various rocks changed by heat from nearby magma / lava. No, Hornsfeld. All right, so you guys do have homework tonight. I did say page 35, but I only mean the chart on page 35. So just this part. We'll probably fill in these if you notice, I've skipped over all of them so far. We'll probably fill these in right before we take the test, a good review. So your homework is letters A through L. Obviously, you'll need your reference table. Yep.